Hello, my name is Robert Pittman. I'm an electrical engineer from Sacramento. Now, let's talk about voltage drop. Let's say we have inverters out here, and they combine into an AC panel. And then we have others down here, and they combine into an AC panel. And then these combine onto an AC panel, as well as more inverters. Something like this. And then it connects to the utility. Power poles, like that. Let's say the service point is 480 volt. Now, we have a certain voltage drop on this point, which is Ohm's law, V equals IR. So you have that 72.2 amps, for instance, if these are assumed to be 60 kW. And then you have a wire size and you have voltage drop. So the current is an assumed 72.2 amps. And where do you get resistance from in an electrical system like this? The wire size. The conductor that we size it to has a certain resistance per foot, and it goes a certain length, and you calculate that out, resistance, and that gets you a volts dropped. So let's say we drop 1.3 volts on this circuit, and then these combine up to a higher current, 72.2 times 3. These have 216 amps and a completely different wire size and a completely different length. Let's say these drop 4.3 volts. And then this one combines up and has an even higher, and let's say it drops 1.8 volts. So the total drop is 7.3 volts dropped. And the inverter is producing 480 volt. So how does an inverter produce 480 volt, drop 7.3 volts, and end at the utility at 480 volt? This is impossible, right? Think of the Escher drawing. I should bring that up just as a visual of water falling, and it goes in a circle and it's always falling and never rising, and it's impossible. Escher is famous for those things. So how does this work? So it works because the inverters are watching the grid. I like to draw my little eyeballs out here. And they're doing whatever the grid is, and it has to fall on. So what it does is it raises the value, the output of the inverter. So instead of 480 in this case, it would be 487.3 volts. A lot of times in solar PV, you'll hear voltage drop referred to as voltage rise, because the net effect is that the inverters have to output a higher voltage. So why is voltage drop calculations important? How do we compensate for that, and how do we understand it, and what's the limiting factor? Why do we care? So let's switch over to a cut sheet of an inverter. This is Yaskawa Selectria PVI 60TL over here on the right. and you'll see an AC output has a voltage range of minus 12% or plus 10%. So let's talk about the plus 10%. So in this case, the inverter is capable of producing 528 volts maximum. So you have to keep your voltage drop below that 10%. Now, I've never heard anybody allow 10%. Most of our customers ask for 2%. The National Electric Code advises basically 5%, and the California Energy Commission requires, I believe, 3%. I believe it's 3%. So we should be able to make that just fine, but you have to know what your voltage drop is, or you could go out of this range accidentally. So what would happen if your voltage drop was out of control on a large system? This has never happened to me, but I've heard of this happening. What would happen is you get a phone call in June, July, maybe August. It's a nice bright day out, but it's not super hot. It's in the 90s, very bright, and you get the dreaded call that says our inverters are shutting off. We have a string inverter system, 1.3 megawatt. We have 9 of these things, and 2 of them are shutting off on a regular basis, and sometimes 3. And that's what's happening, is the voltage drop is so high that it's going out of the output range of the inverter, and the inverter is shutting off. So at the time that it should be producing the best power possible, it's actually shutting down, and that would be horrible. Let's show for the first time on these videos. Let's talk about PV Rocket a little bit. So what I have here is a very quick sketch of a system. I'm trying to figure out how to get it all on the screen at once. Maybe I'll let the modules go off a little bit. So you got modules over here. You tie into an inverter. 1, 2, 3, 4, 5 strings per MPPT tracker. That's what these 3 things are, and we'll talk about trackers in a few minutes. And then it goes AC into a combiner panel, and this is combiner box 1, and then combiner box 1 goes into combiner box 2, as does another 4 inverters, and then the output of combiner box 2 goes into combiner box 3, as well as a 9th inverter, and then it goes into the main switchboard. So I created this just as an example. Let's go in, start PV Rocket, and these are the distances between everything. So from combiner box 3 to the main switchboard is 450 feet. Combiner box 2 goes into combiner box 3, it's 135 feet away. 1 goes into 2, that's 100 feet away. And then these are the branch circuits and so forth. PV Rocket measures all of these for you and puts it right into here. And if you want to change anything, that's fine. You just highlight it and change it, and it's done. It's now 110 feet. So PV Rocket allows you to do that. So everybody that does, let me acknowledge that everybody that does solar, it's very repetitive, the same calculations again and again, over and over. You wouldn't want to do that by hand. So everybody has a spreadsheet. I get that, I understand that. Some people have very sophisticated spreadsheets that they've invested years of their time into, and I respect that, but PV Rocket, if you get it, will help you more accurately and faster because there's no transfer between AutoCAD and your spreadsheet. You you draw out the array, place the blocks for where the inverters are, and then run the program, and it measures everything for you. And there's safety factors that can be put into here, like a safety factor of 10% or up to a maximum of 50 feet and that kind of a thing. And that's all customizable. So here's this. So I'm going to hit next, and the next box is voltage drop. And I was playing around with this, so I'm going to click on this, use minimums right here. So these are the minimum wire sizes on the whole system. PV Rocket calculated all that and put it right into there for me, all done. And it also up here has an estimated cost of $22,000. That there's no labor in that, that's just material, and that's customizable also. Customizable for how much does conduit cost, customizable for how much do these conductors cost, and so forth. So if you look at the way this works is combiner box 2 to combiner box 3 is 2 parallel 700 kcm, and I selected aluminum when I did the chart, and I'm not going to go into how PV Rocket works, so my point is to show you something here. And then this is the percent drop of 0.4%, and here's an estimated cost of materials just for that one run. Whatever the distance is, 2 parallel 7 kcm is $1,974.74. So the up and the down refers to the conductor size. I've had people come in here and say, well, like for instance, this 3.1% on inverter 3, they click the down and nothing happens, and they get frustrated. I don't know how to help them really. The up and the down refer to conductor size. So if you push down, it's already the minimum size for this circuit. You can't go smaller, it'd be a code violation. So the PV Rocket won't let you do it. It stops at number 3 AUG, American wire gauge. And these down here were copper, and there's no indication of that. I just remember selecting copper for the branch circuits and aluminum for the trunk lines. So if I want to bring this into compliance, my customer asked for 2% tops. I'm going to push up, and that's going to go to a number 2 AUG, and the voltage dropped to 2.9%. I'm going to push it again, and it dropped another 0.2% and increased the wire size. So I keep doing this, and you can see that everything is updated real time. I'm up to $23,000, so I've added $1,000 in cost, and just by trying to get inverter 3 into compliance. And I'm going to keep pushing this, and it's getting very hard, and I've got it down to a 2.1%, and I'm at 750 kcm copper. So if I push it up again, it went to 2 parallel 250 kcms, but the voltage drop actually went up a little bit. So I can keep going up, and it's still not 2%. And I'm up to $39,000. I've added $17,000 in cost just trying to get inverter 3 to comply, and I can't. So don't forget that these are cumulative, like I was saying. So if you have 1.3%, so these up here, these voltage drops are not shown as cumulative. They're shown for the segment only. And the reason we did that was to help draw attention to where your worst case is. Yeah, we could have shown this as a cumulative, which would be 0.4 plus this 1.3, and we could have shown it as 1.7 up here and made you do that math in your head and said, well, this is 0.4 then. But we just didn't want to do that. So now we see that there's 1.3 plus 1.4 is 1.7. And then another 0.3 is 2%, and we're trying to get inverter 3 to 2%. It's really not going to make it there ever. you'd have to take this inverter voltage drop down to 0 to get it to 2%. So don't forget this fact. And you can come up here and increase this wire size, and I made that one click, and I have compliance down here on inverter 3. And now my cost is almost $40,000. So let me hit the use minimums again. And one thing that I like to do is I've got 3 parallel 600s. 750 is the biggest wire size that I can buy locally from wholesale houses. So I like to take all of these up to 750 very quickly. And then I can more, and see, look at that. I did that, and I've got compliance on this one all by itself, and I've added $2,000 to the total cost. So it makes everything much easier to get compliance with your customer requirement of 2%. And that one was difficult. I had to go all the way up to 250, but at least it's not parallels. So now I've got complete compliance, 2% all the way across, very fast. I added $8,000 to my total estimate cost. And that's something that PV Rocket does quite well.